Alright, today I'm going to do a quick review of quiz 10 because there seem to be still some confusing, misunderstanding portions. I was very lenient when grading, but you guys should still focus on learning the details because on the final exam she will take off points for basically everything. So here's the problem. We're going to start with full body analysis and just try to determine what W is. Which is pretty straightforward. It's just the area under the distributed load. So it's 2 kips, 2 kip per feet times 9 feet. So a total of 18 kip at halfway down, so 4.5 feet. It's important to figure out how do you want to approach the problem. Do you want to approach it from the left side or the right side? Now, obviously they give you a hint because they give you x starting from the left side. And this is most simple because here you have to find your unknown reactions. So first you have to solve for them, and then solving about that is still more complicated than just starting from the left side. So we're going to start from the left side, beginning with shear analysis. So let's say that I cut the beam somewhere at any point x. I still have my 8. And when I cut, I choose to look at everything to the left. So I still have my 18 kips times feet. I have a distributed load of 2 kip per feet, but some unknown distance x. X can be 1 foot, 2 feet, any distance between 0 and 9. And then I draw in my internal resultant loads, so V, N, and M. It's important to note that this is the standard sign convention. Whenever you cut the beam and look at everything to the left, you need to make sure that V is pointing down, N is pointing outward, and M is pointing counterclockwise. This is where a lot of you got messed up with your signs, and then your graphs got messed up because you didn't have the right signs. So all we're going to do here, first, let's recognize how can we find the resultant load. So resultant load caused by this distributed load is simply 2 kip per feet times x, right? And it's going to be located halfway down. So we're going to have this load here, 2x, at half the distance, because the center of gravity of a beam is half the distance. So then what we can do is we can write some of the forces in the y to solve for our shear force. So we have that negative 2x load because it's pointing down, minus v because that's pointing down as well. So we end up with v equals negative 2x kips. And this tells you that v is going to be linear. Another way you can figure out that v is going to be linear is because this distributed load is constant. Your shear is going to be the integral of that constant. So an integral of a constant is a linear. So then what I can do is I know that my beam starts at 0 and ends at 9. If I plug in 0 and 9 into those 2 points, I can figure out my starting shear and my ending shear. So we just determined the equation for V. So this is the mathematical method. We determine the equation for shear is negative 2x. And all I do from there is I simply plug in points from 0 to 9. And you know, because it's linear, all you really have to plug in is 0 and 9. And you end up with a negative slope. That is a constant slope, right? Constant negative slope, linear. And this slope is increasing in the sense that it's getting progressively more negative, right? Because if you look at the area under the curve, the area is getting progressively larger. And that makes sense because to begin with you have no load, but as you pass through the beam you have another 2 kip per foot, another 2 kip per foot. So you're adding more and more load as you go through the beam. And this makes sense because as you can see the area starts at 0, but as you go through it gets progressively larger and larger. So from here we're going to go and do moment analysis. So now we want to find our moment M once again. So I pin at the cut and I start with 18 kip per per foot, so that is counterclockwise, so that will be negative. Then I need to think about this weight here. It's going to be positive because it's clockwise. No, sorry. So 18 is clockwise. This is counterclockwise, so that is going to be positive. And we said that our force is 2x, and our distance is x over 2. So 2 times x over 2 plus this m, so it's counterclockwise, so it's positive. So in the end, once you go through algebra, you end up with m equals 18 minus x squared. And that tells you that it is parabolic, right? It's going to have, it's going to be an upside down parabola because it's negative x squared. To find my beginning and my endpoints, all I do is I plug in 0 and 9. I end up with 18 and negative 63. Now another important point here is we will be crossing the x-axis because you go from positive to negative. So you need to find the 0 where you cross the x-axis. So that means you just set the equation equal to 0 and you cross the x-axis at 4.24 feet. So let's look at it here. So yeah, I just plugged in 0, 4.24, and 9. So I start at the beginning at 18 kip per feet. Then I know my equation is negative parabolic, so it's going to be a concave down parabola, right? I know that I cross the x-axis at 0, and then I know that I end at negative 63. So, I mean, yeah. So we know because your distributed load is constant, you know that your shear will be linear, and then you know because your shear is linear, if you integrate that, you get to moment. So if you integrate something that is linear, it becomes parabolic, or x squared. So we know that this is going to be parabolic. It's going to have a negative slope, and its negative slope is increasing in the sense that it gets progressively more negative. So once again, as you can see, you have smaller area, but then you get progressively more negative area. So that was basically the mathematical method. You have your equations, all you have to do is plug it in and then plot your points. Another way you could check your work is through the graphical method. So let's look at the beam, right? We look at the beam, and if we start here at 0, you aren't exposed to any load yet. So you automatically know that your shear is 0. As you start moving through the beam, you get exposed to a load equivalent to 2 kip per feet divided 2 kip per foot times the distance. So all you have to do is find the area of this load. So 2 times a total area of 9, that tells you that you are going to end up at negative 18 kips. So you start at 0, you end at negative 18, and because this is a constant, you know that this is going to be linear. So that's how you graphically determine what your shear is going to look like. From there, you can graphically determine what your moment is going to look like, because on the beam at point 0, all you have is 18 kips times feet. So you know that your moment is going to start at 18, positive 18. This is where you guys get confused. Why is this positive if it's pointing clockwise? Because clockwise is typically negative. So yes, when we cut a beam and we do that equation analysis, clockwise is negative, counterclockwise is positive. But when it comes down to graphing it at the very end, you look at this and it is clockwise, but here clockwise is positive. I don't know, I can't explain why. It's just you have to remember that, and that's why it's helpful to have the mathematical method, because with the mathematical method, if you plug it in, your moment comes out positive. So you don't have to think, oh, which sign convention do I have to use? It just comes out positive. If you plug in a 0 here, you get positive. So this, you have to have a little bit more of intuition. So at 0, we have 18 kips. Then what you have to do is find the area under the shear curve. So we do 1/2 base times height, so 1/2 9 feet times -18, that gives me -81 kips times feet. So if I'm at +18 and I have to, from there I have to go down 81. So 18 minus 81, that means I end up at -63. So I know my start point, I know my end point, and I know that because this is linear, this must be parabolic. And I know because this is getting progressively more negative, this must be a concave down curve, because a concave down curve gets progressively more negative as well. So yeah, so you can use the graphical method to check your mathematical method, or you can use the mathematical method to check your graphical method. I recommend doing the mathematical method because it's concrete, you know, it's an actual answer. You're not just guessing and using your intuition. And then use the graphical method to double check that your answers make sense. The biggest problem that most of you had was sign conventions. Whenever you cut the beam, whenever you cut it and you look to analyze everything to the left, you need to make sure that your shear is pointing downward and your moment is pointing counterclockwise. If you had cut the beam and looked at everything to the right, then your shear must point upward and your moment must point clockwise. For most of our analysis, we have cut the beam and looked at everything to the left, so I recommend memorizing this and kind of sticking to using one of these conventions, not both, and not flip-flopping. So I hope that clarified a little bit more